Hello, my name is Dora. I will be presenting brittle or ductile, the effects of print orientation and raster angle on PLA fused filament fabrication tensile samples. The agenda of this presentation will cover all these subsections in the paper. Additive manufacturing or 3D printing is an all-encompassing term for technologies that build parts layer by layer. In this research, we are focusing more on material extrusion, fused filament fabrication, where we use filament push through a hot nozzle layer by layer to create parts. Now, FFF is a very useful tool in the automotive industry with applications in concept models, functional prototypes, manufacturing aids like jigs and fixtures, and layups for carbon fiber parts, and much, much more. Common materials used in these products include ASA, ABS carbon fiber, nylon 6 carbon fiber, and even Ultem 9085. In this work, instead of using those expensive high-temperature materials, we used a cheaper and more accessible material like PLA to explore process parameters and how they would affect tensile strength. That way, we could replicate those same experiments, or lack thereof, in those more expensive materials. We know with additive, we build parts layer by layer, but building by layer can create these anisotropic properties in the final part. Final part performance is thus directly influenced by that microstructure created by the slicer settings. For example, amount of walls we use, the raster angle or fill angle, and all those inner layer voids. Most slicers perform planar slicing, where some process parameters like layer and bead height, wall and shell thickness, print orientation, and infill pattern can drastically vary the performance of our parts. I mentioned raster angle and build orientation, and these are the two key process parameters we're examining further in the research today. Raster angle is essentially the angle that the material is deposited to fill each layer, and the problem with a raster angle that is unoptimized is that it can lead inner layer voids, as shown in this picture captured with a microscope camera. Build orientation is essentially the XYZ position that our part is oriented in and printed on our build platform. The concept with build orientation is that depending on our orientation of layers, this can influence strength concerning the direction of any applied loads. Throughout this research, we referred to samples based on their orientation code, so it's important we define that code. Essentially, when you're orienting in a slicer, you have an XYZ coordinate system, and so we consider the built plate to be X0, Y0, Z0, and anything off that build plate, for example, the image on the right, that's a single angle build oriented in 45 degrees along the y-axis. And then a double angle build would be if I added an X or a Z orientation within that build. So for example, X45, Y75 would be what we considered in this work a double angle. Print orientation is a key process parameter that we often report when documenting mechanical properties. These are two screen caps of data sheets, one from Stratasys and one from Bamboo Lab. We can see that they have considered different build orientations for their tensile strength. When it comes to determining the tensile properties of plastics, we follow a well-documented standard called ASTM D638, but the key thing here is that it's designed broadly for solid plastics, such as ones that are injection molded, and not in consideration of plastic parts that are made layer by layer. So what does this tell us? It tells us that current standards and best practices do not tell the full story of the performance of FFF parts, or even AM parts in general. A solid part made of solid plastic is not the same thing as a plastic part made by layers. Of course, like any research, we had to explore what has already been done, and here's a literature review matrix of previously studied build orientations of FFF samples. Throughout the years, similar cases continued to be repeated. Limited sources were found where print orientation goes beyond the typical ones that are explored in datasheets, so typical would be 0, 90, 45. There was a reference that we found in 2020 where they did explore further orientations like 15 degrees, 30, 60, 75. But again, this was very difficult to find papers where they explored build orientation beyond the typical. Another thing I would like to highlight in this green row is that our publication has been the only one we've been able to source that have considered multiple angle build orientations for our benchmark testing. Why is this a big deal? The datasheets say it's one orientation and we typically print those. That should be good enough, right? These orientations don't represent all real-world applications, where FFF parts have complex geometries or may be designed with non-planar strategies. Considering this, how can we expect a part to perform within these metrics when our final application has layers in different orientations or applied load differently compared to how we tested it? Common print orientations fail to capture the full performance picture of a 3D printed part. And part strength depends on more than just the material we pick. The goal here in this research is then to analyze how our build orientation and fill angle affects the tensile strength of FFF parts, and provide insight to better understand the performance variability in AM. When it comes to our experiment dataset, we have run single angle experiments with varying and constant raster angles, as well as double angle experiments. The summary of this table is that we have 3 build orientations rotated about the y-axis, with varying raster angles going up by 10, between 0 and 30, as well as 45 and 90-degree raster angles. Our single and double angle experiments with constant rasters have explored these double angle orientations, a singular triple angle test out of curiosity, as well as these 3 normal orientations to kind of provide a benchmark for our tests. As I mentioned, we followed the STM D638 tensile testing standard, and we had a 50mm gauge length sliced using Bamboo Studio, fabricated on the in-lab Bamboo Lab X1C in PLA, again by Bamboo Lab. Our testing was conducted on the MTS Criterion Model 43, it's a 50 kilonewton system, and our crosshead velocity was at about 2.5 millimeters per minute during all of our tests. Our elongation was measured with the MTS extensiometer that had a 50mm gauge length, and our Excel software was used for data processing and our stress strain curve generation. Now, our results explore the data through 3 different lenses to kind of understand the trends. We explore the full experimental dataset to get the bigger picture, and then dive deeper into our single angle builds and our double angle builds. In our full experiment set, what we noticed was that strain at break varied up to 20 times, revealing both ductile and brittle behavior of PLA. Our Young's modulus and strain at break also showed the highest variability, indicating sensitivity to the print parameters we were using. I mean, right off the get-go, if you're somebody who's been 3D printing for a while, you already know that build orientation and raster angle play huge roles in the strength of our final parts. What this research further explores is how to quantify just how big those differences are. Our distributions were skewed. Our yield stress had a slight right skew with a higher stress tail, and our fracture stress a stronger left skew, meaning that our weaker samples really influenced the tail. There were a lot of brittle parts. Extreme outliers and variability in some of our samples, considering this is a full experiment and we're kind of comparing single angle builds to double angle builds, made it difficult to use KDE based modeling. This points to relatively complex parameter performance relationships that in the future, moving forward, if we want to train a model on predicting these things, would make it a little bit more challenging predicting single angle builds versus double or triple angle ones. We were curious to see if there was any kind of benchmark or factor in the slicer that could indicate to us whether one sample would have better strength than another in the tensile performance. So we looked at how much material each part would require. The idea that if a part has more material closer to the CAD volume of the tensile sample, it must thus have less voids, right? Unfortunately, when plotting this, we didn't really see a strong correlation between material usage and mechanical properties like strain at break or fracture stress. Identical material usage did not guarantee similar results in our parts, so we couldn't really use this as a ruling measure. Looking at our single angle builds, this is where we took a deep dive in our results and compared those with orientations in only one axis. Our fracture behavior was aligned with raster angle, so parts printed flat broke typically along the raster angle that was used to fill those layers, and that makes sense. We also observed, as expected, that applying tensile force parallel to our layers led to ductile behavior, and perpendicular force caused brittle fracture between layers. Now, if I go back to my introduction slide, this graphic kind of helps make it more sense. Pulling apart perpendicular leads to brittle part performance, where pulling along parallel led to more ductile performance. You can see just by varying that build orientation, we can kind of adjust the performance of our tensile sample, more brittle or more ductile, even somewhere in between. Here are two graphs summarizing our stress strain curves for these single angle builds, where the one on the left includes varying raster angle builds and the one on the right is constant raster angle. What we can immediately pull out of this graph is that with varying raster angle, we get varying stress strain curves. And keep in mind, this is pretty eye-opening considering it's the same material. All the way down to the angle you fill in each layer, you can customize the performance of a part. And that would make sense because your voids would vary depending on how you're able to fill in that layer geometry. With our constant raster angle, you can see that the magnitudes of our curves do vary, but the overall characteristic of the curve with that high slope elastic region, and another varying factor is just how long that plastic region is before we have our ultimate stress, fracture stress breaking point. From these single angle builds, distinct material responses were observed based on build orientation. Only our flat built parts, particularly the one with a 45-degree raster angle, showed this ductile behavior. All other conditions resulted in brittle fracture in comparison to that. Strain at break was bimodal and right skewed, confirming our different fracture modes, and then we have our brittle versus ductile split, which was strongly dependent on the raster angle and build angles, as we see in these graphs. Young's modulus was greatly affected by the y-axis rotation, and we can confirm this knowing we have varied build orientation in y-axis for our single angle builds. Our average Young's modulus for this PLA material was about 2.7 kilonewtons per millimeter squared, with a range of 0.8. Notable variability for our 15-degree build angle, where our standard deviation was greatest. It's clear through our plotted data regarding variable rasters that further testing needs to be done between our 0 to 30-degree raster range, as from these two graphs we see quite a bit of variability within those angles. There's a clear transition zone that exists between ductile and brittle behavior. And future experiments, when we go more in depth in designing our experiment set, should target this range to better understand how the performance is shifting. Moving on to our double angle builds, we noticed more brittle behavior compared to single angle builds. Our average strain at break had dropped to 0.026 with a lower standard deviation, which indicated to us more brittle performance. Our Young's modulus also averaged at 2.7 with a greater range. It had similar stiffness to some of our single angle builds. We can also see the varying stress strain curves of these double angles. If you do recall, there was one triple angle test that was also included in this comparison, but we can see too here that the characteristic curve varies for different parts. Keep in mind that, again, this is all the same material. We see this directly in some of the images of our parts after failure. One thing we didn't expect was some of the plastic deformation we would observe on our parts. For example, experiment 4 in this photo showed zebra stripe patterns. Our build orientation included decimal angles, which probably gave us the zebra stripe pattern due to delamination between our raster fill and our two wall passes that we use. This suggested to us that decimal angle orientation can cause uneven stress distribution and localized failure. We explored this out of curiosity, and in the real world you might not be typing decimal build angles when you're orienting your part, but the CAD data of your part might include different angled geometries, parts branching off, to which when you print in layers and apply load, they might perform similarly to how some of these build angle tensile tests would. Looking at experiment 2, our X130Y15Z0 gave us what appeared to be balanced performance. Looking at our fracture zone, or at least the gauge region of this part, we see an even essentially weakening of the part from that lighter discoloration. It had the highest ultimate stress and strain at break, which was 2 times the average that we observed. And it also showed the highest Young's modulus, suggesting a very rare combination of both stiffness and also ductility, which tells us that there are unique build orientations or process parameters ideal for applications that need both a little flex and stiffness. Our double angle builds gave us clear brittle versus ductile separation in the stress data. For example, in our ultimate stress distribution, it showed a distinct divide between our low stress samples, which had brittle performance, and our high stress samples, which were more ductile. This fracture stress shows a parabolic trend with respect to x-axis angles, where the peaks happen between our orientations of 0 to 60, indicating there's a possible build window that's more optimal for strength, where build orientations that move greater than 60 degrees may really not affect the part performance in a positive way. Discussion on voids. Void formation is a known issue in our material extrusion and FFF processes and is a key source of crack initiation and propagation in a part. And unlike casting, void locations in AM are predictable and repeatable because the same slicer settings would give you the same toolpath, but currently there is kind of a lack of standard methods for both detecting those voids and analyzing how they would affect the final part performance. These internal voids, often caused by the toolpath and the process parameters, significantly weaken the part, or at least offer more variability, which is what we see in the data from varying raster angles. Here are some close-up shots of some of the failure zones of our parts. Microscopic imaging confirms that void patterns vary with raster angle and build orientation. And we can see that some of those raster angles result in bigger and more severe voids per layer. No existing workflows currently integrate this void data into FEA or quality models, and that is a major research gap. Capturing void geometry from slicer outputs and simulating as-built models could enable us to design and predict our part performance a lot better. So solving the issue here would include defining void characteristics, developing methods to extract this void data as in location, centroid, size, and then further using that data to explore toolpath-based mitigation strategies, whether that's gap fill, whether that's varying raster angle within a layer. In conclusion, is PLA brittle or ductile? Well, clearly, we've seen that based on process parameters, it can actually be both. Small changes in build orientation and even raster angle significantly impacted mechanical performance. Standard testing angles, like those we see in datasheets, such as flat, vertical, and 45 degrees, don't capture the full variability. Unexpected results in performance can be expected. Although clear trends have been observed, more tests need to be done, especially if our goal is to, in the future, train a model or to basically understand the full performance range of a material based on selected process parameters. There is room for quite a bit of future work regarding this topic, whether that's refining the design of experiments and analyzing our voids directly from the slicer images. We can further expand our framework, whether that's for different material types, different AM processes, and different mechanical tests such as compression, flexural, impact data. Long-term goal is to collect all this data and develop a predictive tool where users can input their material type and print parameters to generate stress-strain curves in performance. Support vector regression seems to be a promising approach for modeling nonlinear behavior from limited data, and I've begun to explore this for one of my course projects. The idea of using a predictive tool is that it would reduce slicer prep time and improve decision making for both engineers and technicians. Here are my references in case you're curious. Any questions?